Okay, so let's continue the example. Let's we have three random sample random sample of size 3 actually. Okay, from a distribution with unknown mu, where the range of mu is this one, and where the variance is known. Variance is sigma square and it is known. Positive number. Okay, which estimator? Let's say theta 1 had is x bar, or theta 2 had is given as 2x1 plus x2 plus, okay, let me write it again. Okay, so 2x1 plus x2 plus 5x3 over 8 is a better estimator of mu. Okay, so in such cases you have to consider mean square error. Okay, and then you have to find the expectation of these two estimators and also the variance of these two estimators. Then you have to calculate the mean squares and compare which one is smaller. Smaller one is the better one. Okay, so let's find the theta 1 hat. It is expected x bar, which is mu. It's an unbiased estimator already. Okay, so when we consider the second one, expected 2x1 plus x2 plus 5x3 over 8. So we have 8 mu over 8. So this is also unbiased estimator. So they are both unbiased. So which one is better now? Both of them are unbiased estimators of mu. So let's consider the variance. So variance of theta 1 hat will be sigma square over n because it's x bar. Variance of theta 2 hat will be 4 sigma square plus sigma square plus 25 sigma square over 64. Okay, so we have 30 sigma square. Actually, this is sigma square over 3 because n is 3, 64. When you calculate, you will see that this is bigger, this is smaller. So when we calculate the mean square errors, mean square or error of theta 1 will be variance of theta 1 because they are unbiased estimators, and similarly mean square error of the second one is also the variance of the second estimator. And when we compare the variances, actually this is bigger, the second one. So mean square error of theta 1 for estimating theta is smaller than the mean square error of theta 2 hat. Theta 1 hat, which is x bar, is a better estimator of theta. Okay, let's consider another example. With the examples you can understand better. The idea is basically very simple. Okay, so the parameter space is given as theta such that actually this one. Again, let's say we assume that we have a random sample. For this case, actually, we already calculate the MME of theta, if you remember, was 2x bar. Okay, and when we consider the MLE of theta, we obtain it as theta hat x bar. So which one is better estimator? Okay. So let's calculate the first expectation of theta tilde. It is 2 times expected x bar. So for uniform distribution, expected x is theta over 2. For x bar also the same. So it's an unbiased estimator. Okay, so let's find the variance. Variance of theta tilde. It is 4 times variance of x bar. For uniform distribution, again, the variance is theta square over 12n, and is from x bar. So it is theta square over 3n. Okay, so we both find the expectation and the variance. Bias is 0. So this will be exactly the mean square error of theta tilde. Okay, so let's find the expectation of xn bar here. Okay, okay, so let's first find the PDF of xn. So it is, if you calculate, you will see that it is this one. Okay, let's find the expectation. Expectation of xn is obtained as this one. So it is not unbiased estimator. It is not an unbiased estimator of theta, but it is an asymptotically unbiased estimator of theta. Okay, so we can calculate the bias. Okay, so expected theta hat minus theta, and n plus 1 over theta minus theta, so minus theta over n plus 1. So this is the bias. So calculate expected xn squared to be able to find the variance. So if you do the calculations, you will get n plus 2 theta squared. Okay, and variance of x bar then obtained as expected xn square minus expected xn whole square, and we obtained the variance as n plus 2 n plus 1 square theta square. And if you calculate the mean square error of theta hat, so it is the variance of theta hat plus the bias by definition. Okay, then the variance of theta hat is this one, n plus 1 whole square theta square, plus we obtain the bias as minus theta n plus 1, right? This is 1. Take the square, and then when we calculate, we obtain 2 theta square n plus 2 n plus 1. Okay, so let's compare them. So mean square error of theta hat, theta, we obtain it as 2 theta square n plus 2 n plus 1. And mean square error of theta tilde, what was that? Where is it? Okay, so theta over 3n. So denominator here is n square or something for this case, so it is smaller. So here, although MLE is not an unbiased estimator of theta, so theta hat, which is an order statistic, is a better estimator of theta, although it is not an unbiased estimator of theta. Okay, we have another concept known as mean square error consistency. Actually, both concepts are the same, consistency and mean square error consistency. For me, they are exactly the same actually. So Tn is called mean square error consistent or consistent in quadratic mean if expected whatever the estimator is minus t square converges to 0 as n goes to infinity for theta in the parameter space, all theta values. So we have a theorem. So Tn is consistent in mean square error if and only if you can see the rules are almost the same. We don't have expectation only here. N goes to infinity, and when we consider the limit, when n goes to infinity, variance of Tn is 0. So if these two conditions satisfied, oops, these are the same, sorry, I should say expectation here, expectation, it should be theta. So if these two conditions are satisfied, then we have consistency in mean square. But actually these two conditions are also true for regular consistent estimator case. So basically we can use the same cases. So basically consistency in mean also means that we have a consistent estimator. Okay, so if T sub n is consistent in mean square error, then this also means that Tn is a consistent estimator of theta. Okay, so then we can talk about relative efficiency. RE. So again, we are using this to be able to compare two different estimators. So let's say we have an unbiased estimator, relative efficiency of an unbiased estimator of g theta, to another unbiased estimator t star of g theta. G theta can be just theta actually, but for any other function of the parameter we can calculate the relative efficiency. So the relative efficiency of t, which is an unbiased estimator of unknown parameter, and another estimator which is t star for estimating g theta, is the variance of t star over variance of t. So unbiasedness is a good property actually. So we are putting the variance of the unbiased estimator in the denominator to see which one is better. So if the relative efficiency is just 1, so these are equivalent actually. But if we have an unbiased estimator t star of g theta is said to be efficient. Okay, so to be able to say that our estimator is efficient, then its variance should be lower. If the variance of t star is less than the variance of t, okay, so this means that this relative efficiency should be less than 1, right? So if this is the case, we have an efficient estimator. If the relative efficiency of t and t star for estimating g theta less than or equal to 1, equality is just shows the equivalency actually for all unbiased estimators of g theta. Okay, So we use sometimes ET notation to represent that, sometimes this notation, okay, or just capital efficiency. So it is the efficiency of it can be an unbiased, it can be another estimator, not just the unbiased estimator actually. T of g theta efficiency of an unbiased estimator T of g theta T star, let's say, is less than 1 for all unbiased estimators, then we can say that T star is the efficient estimator of g theta. Okay, so this shows us the unique best estimator actually, but you have to consider all possible unbiased estimators and their variances, and you have to show that the variance of T star is less than all the other variances of all other unbiased estimators. So it's not that easy to do that actually, so we have different approaches. So let's consider an example. Let's say we have a random sample of size n again, from exponential I from 1 to n. If I say IID like that, this means that we have a random sample. So consider two unbiased estimators of theta. One of them is x bar, the other one is n first order statistic. So when we consider the expectations actually, so we will see that expected x bar is theta, expected n times x1, so when you calculate it you will see that it's theta. So both of them are unbiased estimators. Okay, so let's check their variances. Let's compare their relative efficiencies of x bar and n times first order statistic. So relative efficiency of theta for these cases. So find variance of x bar and variance of n x1. So this is theta square over n. When you calculate, you will see that it is n square theta square over n square. So we will obtain 1 over n, which is less than 1. Because n is the sample size, it should be greater than 1, you know, or equal. Let's put an equal to size for n equals to 1 case. So this means that since relative efficiency of theta for these two estimators is less than 1 and x1 is a poor estimator, or x bar is a better estimator, or x bar is a better estimator of theta. Okay, so this is another approach actually to compare two different estimators, but these gives us just the better estimators, not the best ones. To be able to say the best, we have to consider all possible unbiased estimators of theta and then show that the variance of one estimator is less than all the other variance of all the other unbiased estimators. So this is not very efficient way to do that actually, so we have different rules. Okay, so let's start the sufficiency. So this is very important topic actually. So being estimator, a sufficient estimator. So here we are trying to find an estimator which has all possible information to be able to estimate the unknown parameter from the sample. Okay, so we want to find an estimator who has all possible information regarding the sample to be able to find to be able to estimate a parameter. So when we have the sufficient estimator, basically we don't have to know all sample points. Actually, just knowing the value of the sufficient statistic will be enough for us to be able to estimate a parameter. So it's very powerful statistic. Okay, so if we don't have just all x1, x2, xn, we can we can find a good estimator using a sufficient estimator. So here basically our question here, can specific statistic replace the entire data without losing important information about the parameter or parameters. So our basic question is that one. So we want to reduce our dimension. Okay, so we have a dimension of n, so we have a sample. Okay, n dimensional space. So we want to reduce it to 1D or 2D. Okay, so just find sufficient statistic. Okay, so we want to reduce our n dimension to 1 dimension or 2 dimension by using this sufficient statistic. So this sufficient statistic have all possible information in the sample to be able to estimate the parameter. So statisticians generally look for ways to reduce a set of data so that this reduced form can be more easily understood without losing the meaning associated with the entire set of observations. So if I don't have all these sample points, if I just have this sufficient statistic, then I have all possible information and to estimate parameters, and actually I don't lose any information. Okay, so from n dimension to 1 dimension or 2 dimensions. So sufficiency provides us a reduction of a data set to a concise set of statistics without losing information about the parameters. Okay, so we have x random variable. PDF is given to us, we know the PDF. So theta in the parameter space. So first of all, we focus on the single unknown parameter case, then we will increase the parameter space. Unknown parameters. Okay, so then let's say we take a sample from this population. Sample random variables. Okay. Then consider a statistic y is a sufficient statistic for a parameter theta yazabilseydim keşke. If y contains all the information available in the data about the value of theta. Okay, so consider that. So we have a statistic it has all possible information. So when we know the value of y, so there will be no more information left in the sample actually. Okay, so it has all the information inside. So let me stop here. I will continue this subject and how to find sufficient statistics in two different ways in the next video.